Connecting a powerful language model directly to a physical robot sounds like the ultimate shortcut to intelligence, but it triggers a critical latency trap that makes real-time manipulation impossible without a hybrid architecture. While recent research suggests we can shave roughly 7% off communication delays by optimizing command parsing, this improvement remains insufficient for high-speed physical control where every millisecond counts. The fundamental engineering reality is that large language models inherently introduce non-deterministic processing delays ranging from hundreds of milliseconds to seconds, which fundamentally breaks the stability required for precise manipulation tasks. Today, we unpack why streaming tokens directly into a robot's motor loop creates instability and how the industry is solving this with dual-layer control systems. The confusion between chatting with a machine and controlling one stems from treating an LLM as if it were a simple decision switch rather than a heavy computational engine. When you connect Reachy Mini to GPT Realtime 2, you are essentially asking a system designed for semantic reasoning to perform time-critical stabilization duties simultaneously. This creates a mismatch in timescales where the physical world moves much faster than the model can think. The robot's sensors might detect an approaching obstacle or a slipping grasp at one moment, but by the time the LLM processes that visual data and generates a safe command, the environment has already changed. This decoupling of the robot's actual state from its reasoning context is what engineers call the latency trap. Consider the specific mechanics of this failure mode. If you attempt to stream large language model tokens directly into Robot Operating System version 2 without an intermediate middleware layer or parallel processing, you reduce command parsing overhead but fail to address the core inference latency. The LLM itself remains too slow for sub-second reactive control loops. In a high-speed manipulation task, even a delay of 300 milliseconds can be catastrophic. A robot arm moving at standard industrial speeds might travel several centimeters in that window alone. If the model decides to stop or reverse course based on an outdated sensor reading from half a second ago, it may command the motors to brake while the inertia carries it into an obstacle, causing damage rather than preventing it. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The statistics behind this limitation are stark and non-negotiable for physical systems. Research indicates that direct integration of GPT with ROS2 enhances human-robot interaction only for slow, deliberative tasks like navigation or high-level planning. It simply fails to meet the sub-millisecond response times necessary for dynamic physical interaction where stability is paramount. A pure LLM control loop is non-viable for these high-frequency tasks because it cannot guarantee deterministic timing. The output of a probabilistic model varies in length and generation time, meaning you cannot predict exactly when the next command will arrive or how long that delay might be on any given iteration. This variability introduces jitter into the feedback loop, making smooth motion control impossible without external smoothing filters that essentially negate the direct connection speed benefits. Consequently, the industry is moving toward hybrid architectures where fast, deterministic controllers handle immediate motor commands, while LLMs operate on slower timescales for high-level planning and semantic interpretation. In this design, a low-latency controller manages the stabilization of the robot arm or leg at thousands of cycles per second, ensuring that balance and grip are maintained regardless of what happens in the cloud or local inference engine. The language model acts as an asynchronous supervisor, interpreting complex instructions like "pick up the fragile object" and translating them into safe waypoints for the low-level controller to execute. This separation prevents the latency trap where delayed feedback causes instability or damage because the physical system is never left waiting for a semantic decision during critical moments of motion. However, we must acknowledge that current benchmarks focus primarily on navigation rather than dexterous manipulation, leaving a significant knowledge gap regarding precise thresholds. We know generally that delays beyond a certain point break stability, but there remains limited empirical data defining exactly how much latency different robotic platforms can tolerate before control fails during complex grasping or walking tasks. Without this quantitative substantiation across various hardware configurations, the claim that LLMs are universally unsuitable for real-time control is slightly too broad, though practically sound for high-speed applications. The engineering reality dictates that until we have specific data defining these limits, assuming an LLM can replace a PID controller in a dynamic loop remains a dangerous hypothesis rather than a viable strategy. The path forward involves acknowledging the distinct roles of different computational layers within autonomous systems. We cannot simply plug a chatbot into a motor driver and expect it to function as a general-purpose brain for physical interaction. The solution lies in respecting the physics of motion versus the nature of language generation. By separating the fast, deterministic layer that handles immediate safety and stabilization from the slow, semantic layer that handles intent and planning, we achieve both intelligence and reliability. This hybrid approach allows robots like Reachy to perform complex tasks with human-like reasoning while maintaining the split-second reflexes required to interact safely with a dynamic world. It is not about choosing between speed or smarts. It is about architecting systems where each operates at its optimal timescale without compromising the other. The lesson from connecting GPT Realtime 2 to Reachy Mini is that raw intelligence does not equate to real-time control capability. The latency trap is a fundamental constraint of current architecture, and overcoming it requires more than just faster models or better internet connections. It demands a structural shift in how we design the interface between software reasoning and physical action. As these systems evolve, expect to see increasingly sophisticated hybrid frameworks that seamlessly blend high-level planning with low-level reflexes, creating machines that are not only smart but also physically competent in real-world environments. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.